Today's lesson is 3.2, Logarithmic Functions and Their Graphs. Before we start any examples, I felt like the best thing to do for today was to review transforming exponential equations into logarithmic equations. And I'm just going to make up something that is a true statement and review transforming these with you like we did last year in Algebra 2. So let's take something like 5 squared equals 25. That is obviously a true exponential statement. So if I want to take that and turn that into a logarithmic statement such as this, then I can use a little rule that I used last year in Algebra 2, use a little left, right, left technique, and I can transform this into a logarithmic equation. We read this as 5 squared, 5 being the base, so when I do a logarithmic statement, 5 stays the base. This would be log base 5. The left means the 5 stays on the left side of the equal sign. The 25 comes to the left hand side of the equal sign, and the 2, which is the exponent, goes to the right hand side of the equal sign. That's where the left, right, left comes in. The 5 and the 25 are on the left hand side. So now I have log base 5 of 25 equals 2, and there's your logarithmic statement. Now if I start with this logarithmic statement, this is a log statement, and I want to turn this back into an exponent, you can also use the left, right, left technique, and you can turn it right back into an exponential statement. This is log base 5 of 25 equals 2. You can still do left, right, left, log base 5, so 5 is the base. The 2 comes to the left as the exponent, and the 25 goes to the right as your answer. So 5 squared equals 25. Exponential to log, back to exponential. So that's just a quick review of what we did last year in Algebra 2. You may not have learned it with the left, right, left, but that's just one option of a way to remember how to transform those. So let's start down here with number 1, and we are going to evaluate, which means we are going to calculate what this answer would be. Log base 4 of x when x is 16, so put a 16 right here. Log base 4 of 16, so we pretty much want to just figure out what that answer would be, so put equals question mark. I really don't want to put equals x because I just had an x there that I filled in with 16, so I'm just going to put equals question mark. So let's go left, right, left, and let's figure out what we're trying to figure out. 4 to some power is 16, so that's why I'm trying to evaluate this for what exponent of 4 gives me 16. Well, that would be 2. So there you go. What exponent of 4 gives you 16? Now if that wouldn't have been an x, I probably would have put equals x, but I'm just going to put equals question mark for now. So let's move on to the next one. Log base 3 of x when x is 1 over 81. Log base 3 of 1 over 81 equals something. Left, right, left. So 3 to some power equals 1 over 81. Well, what exponent of 3 equals 81? You'll have to try to figure that out. And because the 81 is in the denominator, that lets me know that it's going to be a negative exponent. So the exponent of 3 that gives me 1 over 81 ends up being negative 4. Now, we will end up reviewing the change of base formula later on, but I think now would be a good time to talk about change of base for this answer right here, how you would calculate this in your calculator. Like I said, we'll talk about it more later, but I want to go ahead and review change of base. Yes, you need to be able to do this without the calculator, but now would be a good time to review putting this in the calculator. The calculator, when you hit the log button, that log button is an understood log base 10. Well, this is not log base 10, so you must use the change of base formula. And for those of you that have forgotten it, this means you would type in log 16 divided by log 4. So I'm going to pull my calculator up. We know the answer is 2. So I'm going to pull my calculator up. This would be log 16, close out your parentheses, divided by log 4, and the answer is 2. So just a quick refresher, and we will discuss change of base formula more later. But that turned out to be 2 right there. The same thing we did without a calculator. So for number 3, we are actually going to use a calculator for this one. Now this is just says log. Notice right there there's no base. If there's no base, it is an understood 10. So that is log base 10 of x when x is 100. So this is log base 10 of 100 equals something. Well, even though it says use a calculator, this one, technically we don't need a calculator. We'll type it in there in just a second. But look at this. Left, right, left. Can't you figure out what exponent of 10 equals 100 without a calculator? That one's pretty obvious. But even though, since it said use a calculator, let's go type this in the calculator. Remember, the log button is log base 10. So since this is log base 10, I can go back to my calculator, and all I have to do is hit log 100, since it's already log base 10, and it gives me 2. So let's try this one. Log understood base 10 of 1/5 equals something. Now I'm not going to try to figure this one out like we did this one without the calculator. So I'm going to go back to my calculator screen, and I'm going to type in, I'm going to hit my log button for this, and then type in 1/5. Log 1/5, and let's round to 4 decimal places. So since I want 4 decimal places, I'm going to look at the 5th one here. The 7 makes the 9 round up to a 0, which makes the 8 round up to a 9. So negative 0.6990. Negative 0.6990. For this next set of examples, we have 4 properties of logs we can look at. But if we will continue to solve these 3 like the other set we just did, we really don't need to analyze these properties, but they're there if you would like to go back and look at them. So on number 5, we have log base 5 of 1, but we don't have equals anything. So if you'll just put like equals x here, or equals question mark, like we had on the other ones, equals question mark or equals x, and then we're just going to come back through here and solve for what's missing, and then you'll see that they just kind of follow along with the other examples we did. So let's come over here and let's go left, right, left. So 5 to some power equals 1. Well, what's the exponent of 5 that equals 1? What exponent always equals 1? Well, that exponent is 0. Anything to the 0 power is 1. Number 6. Left, right, left. Square root of 11 to some power equals the square root of 11. What exponent of the square root of 11 is going to give you the same thing? That would be 1. Anything to the first power equals itself. And on number 7, this 8 stays on the left, all this goes to the right, and this comes to the left. So 8 to some exponent equals 8 to the 30th power. what does this exponent need to be to equal 8 to the 30th power? And that would be 30. And that's all there is to it. Examples 8 and 9 use what we call the one-to-one property. I'll write it up there, the one-to-one property. I believe you use that in in notes 3-1, where you would try to get the same base to solve the exponential equations. So if you'll notice on number 8, you have log understood base 10 and log understood base 10, once on the left and once on the right. If that's the case, then you can eliminate the logs and you can just solve for what you have left. 4 minus 3x equals x plus 2. Simple algebra equation from there, so just solve it. 2 equals 4x and 1/2 equals x. Number 9, the same thing. Log base 3 once on the left, log base 3 once on the right. The reason I'm saying once on the left, once on the right is because later on you will have to do some condensing to get it to where you have log base 3 once on the left and log base 3 once on the right. But this is already condensed, you haven't had to do that yet. And so we will just solve for what's left. X squared plus 4 equals 29. Continue to solve. X squared equals 25. Take the square root of both sides. X equals, don't forget this, plus and minus, oops, not the square root, plus and minus, not the square root of 5, but just 5, plus or minus 5. Last lesson, you all talked about exponential growth and decay. We did a lot of those last year in Algebra 2, and you would have something like 4 to the x power. So I want to review real quick because it's going to make a connection between this logarithmic graph, and I want to put two little points on this graph. 4 to the x power. So if I put a 0 for x, 4 to the 0 power is 1. So I'm going to have the point 0, 1 on my graph. That's very important for an exponential graph, the point 0, 1, because anything to the 0 power is 1. And if I put a 1 in for x, then 4 to the first power is 4. So I'll have the point 1, 1, 2, 3, 4 on my graph. And it'll just give me a general idea of my exponential. This would be a growth graph because it would be exponential growing. So 4 to the x power would look something like this pink graph right here, having the point 0, 1 and 1, 4 on there. Now today we're looking at logarithmic graphs, and these two are going to be inverses of each other. Now back in chapter 1 we talked about inverses. We talked about inverses a lot. And to find the inverse of a graph, hopefully you remember that you switch two things. You switch the x and the y, and then you end up solving for y. So look at this equation right here. I'm going to bring it down here. This f of x would be y equals 4 to the x power. So if I find the inverse of that, that would be x equals 4 to the y. Okay, I switched the x and the y. Switch x and y. This is a review. Switch the x and the y. So I'm going to flip this around here. 4 to the y equals x. Alright, let's do our little left, right, left thing here. Left, right, left. Log base 4 of x equals y, or y equals log base 4 of x. Well, check it out right there. Log base 4 of x. That's the inverse. Now if we are switching the x and the y for the inverse, remember to find graphs of the inverse, or to graph the inverse, you can take specific points and you can switch the x and the y coordinates to find the graph of the inverse. So 0, 1 would become 1, 0. 0, 1 would become 1, 0. And 1, 4 would become 4, 1. 1, 2, 3, 4, 1. This is what a logarithmic graph looks like right here. Now, when you come down here, do not cross over the y-axis. Okay, I'll talk about that on the next examples, but what happens is you have a vertical asymptote right here. Okay, your logarithmic graph comes down here and it does not cross over the y-axis. You have a vertical asymptote. But I'm going to point out, I'm going to make these really big and fat. This point right here, 1, 0, this is very, very important on your logarithmic graph. Just like the point 0, 1 is very, very, very important on your exponential graph. Okay, this is very important on your exponential graph. And this one right here is very, very important on your logarithmic graph. So I'm making them really fat, making them stand out here on your examples. So this is your f of x graph, and this is your g of x graph. Now this is easy to put in your calculator, 4 to the x power, and if you want to put this in your calculator, this is when you would have to use your change of base. You would have to use y equals log of x divided by log of 4. That's your change of base formula that I showed you back over here. Right here, your change of base, log 16 divided by log 4. You would do log x divided by log 4 if you wanted to put that in your calculator. Now the reason I put this y equals x line over here, because remember that inverses are reflected over this line y equals x. So you should be able to tell that those are inverses of each other. So in our next couple of examples, we're getting ready to look at some more graphs. Okay, let's try a few graphs and see what happens here. We're going to describe some transformations of the graph log base 3 of x, and we're going to graph the new function on the same graph of f of x. We're going to state the domain, the x-intercept, and the vertical asymptote. Okay, so we're going to state several things. So underneath each graph, let's go ahead and write domain, vertical asymptote, and x-intercept. Squish that in here. X-intercept. Okay, and we're going to state that for everything. Now remember, back here on this example, what point did I say was very, very important for logarithmic graphs? I made it really fat. Right here, the point 1, 0 on all logarithmic graphs. So right here, 1, 0, 1, 0, 1, 0. What you see graphed here is log base 3 of x. Alright, that's what you see graphed. That's kind of like your parent function. And then what we're going to do is we're going to do these different transformations to each graph, and then we're going to see what happens. But this is the starting point. Now in addition to that, what you don't see, and I'm going to sketch on here for you, is we don't see the vertical asymptote. I'm going to draw it on here. It's this little vertical dotted yellow line. So as we shift the graph around, we also need to keep in mind that this vertical asymptote, I'm going to draw it here on all of them, this vertical asymptote needs to move along with the rest of the graph. So you need to move the vertical asymptote along with everything else. Okay, it's kind of, they go together. This with that point and your vertical asymptote, well, I didn't draw that very good, your vertical asymptote, let me try that better. Your vertical asymptote and your logarithmic graph, they stay together. Okay, they move together. So log base 3 of x and then the -1 on the outside means the graph moves down 1. That's your transformation. So take this graph, shift the whole graph down 1. So this point right here gets shifted down 1, and that's where that point is. And we need to see this point has been shifted down 1. Now, as this vertical asymptote moves down, it's vertical. As it moves down, does it really change any? No. A vertical line shifted down is still going to be at the same place. So your vertical asymptote started at x equals 0, and it's still at x equals 0. Okay, that one didn't go anywhere. Now, I am going to kind of draw this sort of like that. Now, it's kind of hard to kind of estimate because we have to say the x-intercept. I may have to go back and adjust this, and this may not have been the easiest example to start with because we're going to have to actually calculate, and I'm going to come over here. We're going to have to calculate the x-intercept for this problem. We won't have to do it for all of them, but for this one we're going to have to calculate the x-intercept for number 11. Okay, but let's talk about the domain for just a second. If I have a vertical asymptote at x equals 0, then my whole graph is going to start at 0 and it's going to go to positive infinity. But I will have a parenthesis at 0 because my graph is not going to ever touch right here at x equals 0. It's going to keep getting really, really close to it, but it's never going to touch it. Now, the way I drew my graph, I mean, I could have curved it a little more up here. It could have crossed at 2, could cross at 3. You know, it just kind of depends on how I draw my graph right here, where my x-intercept is going to be. But I want you to calculate it and tell me exactly where it's going to be. So the way you calculate that is you take your equation, log base 3 of x minus 1, and you set it equal to 0. And we're going to solve it. Log base 3 of x equals positive 1 because you add 1 to 0. Left, right, left. 3 to the first power equals x. 3 to the first power is 3. So your x-intercept is 3. So my x-intercept would be at the point 3, 0. So I can draw my graph a little bit better. Make sure that it crosses exactly where it should at positive 3, 0. Have that point down there. And there's that logarithmic graph. Because I shifted this down, I had to calculate my x-intercept. Let's try number 12. Same thing, I'm starting off with my 0.10. I'm starting out with my vertical asymptote. This x plus 2 in parentheses will move the graph to the left 2. So everything shifts to the left 2. Everything. Let's start off by shifting the vertical asymptote to the left 2. If it started at 0, then I'm going to move it to the left 2. So it's going to be right here at negative 2. Be right here at negative 2. So I'm going to go ahead and write that down, that my vertical asymptote is at x equals negative 2. Now, if this point right here was originally at 1, 0, shift it 2 places to the left. 1, 2. Right there. Now think about this. If all you're doing is sliding this 2 places to the left, isn't it pretty obvious where your x-intercept is? You didn't move it up or down. You're still on the x-axis. It's pretty obvious where your x-intercept is. It's at the point negative 1, 0. So you can go ahead and draw your graph. Just have it follow this one as close as you can. Just make sure that this point is very obvious. And if your vertical asymptote is at x equals negative 2, the domain is going to be from negative 2 to positive infinity with a parenthesis at negative 2. And we have one more. We have a negative in front of log base 3. A negative in the very front means we're going to reflect the x-axis. So if we reflect the x-axis, my vertical asymptote is going to reflect over itself, so it will still be the same vertical line reflected over itself, so it's still x equals 0. This will reflect over the x-axis. This point 1, 0 will still be at 1, 0, but your graph will now look like this. Your x-intercept will still be at the point 1, 0, and your domain will be from 0 to infinity. Make sure, though, that you draw your vertical asymptote on your graph. Make sure that you state your x-intercept. I only had to calculate it for number 11 because I shifted the graph up or down. It's very important that you draw your vertical asymptote on your graph. This next section is dealing with natural logarithms, and this is going to be new for many of you. We did not discuss this in regular Algebra 2 last year. Ln stands for natural log, and that's also known as log base e. Now back in Chapter 2 we discussed the number e, or e standing for a specific number. So that will hopefully help you understand natural logs a little bit. We'll work with natural logs a lot like we did regular logs, and we still have some of the same properties. There's a lot of different ways to handle natural logs, but I'm going to approach it a different way than some people do. I'm going to approach it the same way I've done some of the other ones, just to keep it consistent. So what I'm going to have you do is anytime you see ln, I want you to replace it with log base e. So that way we're going to approach it the same way we have done everything else today and all of our other logarithms. So down here when you see ln, let's replace that with log base e. Alright, that means log base e of e to the 1/3. Okay, ln was log base e, and let's figure out what that means, or what that equals actually. So let's go left, right, left. So e to something equals e to the 1/3. What exponent of e equals e to the 1/3? That would be 1/3. Okay, let's try number 15. ln is log base e. So I'm going to do 15 times log base e of 1. Well, let's kind of ignore the 15 for a second. We'll deal with that in just a minute. But let's do log base e of 1. Alright, let's figure out what this is. E to something equals 1. What exponent always equals 1? That exponent is 0. Now let's come over here and multiply that times 15, and that would equal 0. Okay, let's try number 16. ln is log base e of e over 6. So let's simplify the numerator, the top part. Let's figure out what this equals up here. So left, right, left. E to something equals e. What exponent of e equals e? Think about that. What exponent of e equals e? Well, that would be 1 over 6 is 1/6. And looks like we have one example left. Alright, let's try the graph of a natural log. The graph of a natural log is very similar to the graph of a regular logarithm. If the graph of a regular logarithm has that important point 1, 0 on it, that point 1, 0 on it, a natural log will also have that point 1, 0 on it. Okay, I'm going to just kind of, I wish I could pencil it in. I can't pencil it in, but I'm going to kind of sketch your original graph, and you have your vertical asymptote at x equals 0 to start off with. So this natural log of x plus 3 means we go to the left 3. So let's move everything to the left 3 places, including your vertical asymptote. So your vertical asymptote is now going to be right here at -3. And your graph will now be at, move it to the left 3 places, 1, 2, 3. So it'll be right here. Make this bigger. Kind of scribble that one out. Left 3. Now we sketch the graph of it. Make sure you get your asymptote on there. Make sure this point is obvious. That was originally at 1, 0. And we are asked to find the domain. So you need to know where your vertical asymptote is to give me the domain. If your vertical asymptote's at -3, then your domain will be from -3 to positive infinity. And that is our last example for section 3.3. Scratch that, not 3.3. We just finished 3.2. 3.3 is coming up next.